Today we're going to talk about the different forms of energy and conserving energy. Okay, we don't mean like turning off the lights or closing the door. We mean like transferring energy from one type to another. There's a lot of different ways to talk about energy forms. You can see there's a picture on the right hand side that has some of them. Ours are going to be like this, they'll be slightly different. We're going to outline what those are like for you. What do we mean when we say energy? Well, energy is a very human idea. There's no energyometer that you can use to actually measure how much energy there is in something. No matter what science fiction movie you see, it makes it seem like such a thing exists. There's no such thing. It's really a human idea. In fact, it was developed during the late 1700s, early 1800s during the Industrial Revolution as a way for people to be able to track how much work or how much stuff was being done by machines. What it means is it's a substance that's going to make something apply a force to push on something across a distance. So it's going to push on something, and by pushing on something, it's going to make something else move some amount. That's what energy does. It's going to make something move a certain amount. Now that could mean anything. For example, gasoline. Well, it seems like, well, does that make that it seems like, well, that doesn't seem like the same thing. But if you think about it, you take a little gasoline, like coming out of the pump on the left, you attach a flame to it, some sort of fire, and it applies a large, and a little air also, and it applies a large force to air molecules or whatever is around it across a large distance. You can get a large flame, you can get a large push, and if used or harnessed correctly, you can use it to move all kinds of things. We use it every day. If you use a car or a truck or take a bus, any type of vehicle that you use takes that force, that small amount of force, actually it's a very large amount of force per ounce of material, ounce of liquid, and pushes it across a distance to make something move. So that's what we mean when we say energy. It's anything that will make a force across a distance. And we're going to look at some different forms of it now. Okay. How do we know something has energy? Well, we just look at it and we look at where forces are being applied or may be applied if allowed. So we're not just going to look at if the force has been applied, we look at can it be applied if the circumstances are right. If, say, in this case, gasoline in the pump doesn't have any energy being used while it's in the pump, not until it's put in your car and the spark is applied inside the piston is the force going to be from the gasoline going to be freed from the molecules inside of it. So we're not just going to look for if force is being applied now. We're going to look for if it can be applied if we put the circumstances in the right place. The first form we're going to look at is thermal energy. By thermal energy, we mean the energy of moving molecules. Well, thermal, if you're used to your root words and all that stuff, what we mean by that is moving molecules. You can see that in the picture below, we've got a bunch of molecules. They're all moving around. The longer arrows, like it shows in the picture, means higher speed. So the faster ones are moving around. The slower ones aren't moving as much. Well, thermal to us means heat energy. The faster the molecules move, the more heat they have. The more they bang into us, the more energy they're going to impart to us, the warmer we're going to be. When we turn up the temperature in our homes on a cold day, we're making the molecules move faster around our house. So they bang into us more often. They transfer more energy to us. They make us warmer. And you can see in the example here a few different ways that thermal energy gets transferred. You can see that in the example of the campfire, it's giving off energy in terms of radiation. That's actually a different kind of energy. We're going to classify that as light energy. Conduction, in other words, the moving molecules are going to be in the handle. They're going to transfer the person's fingers. Convection, you can see in the molecules inside the water in the pot, basically the molecules are going to bump into each other inside the water, and they're going to carry the heat, the thermal energy, because the molecules at the bottom of the pot are going to move a lot faster than the ones at the top. They're going to bump into each other and transfer energy from the fast-moving ones at the bottom to slow-moving ones at the top. So eventually the whole pot of water will be warmer. We'll have molecules that move at a faster rate. That's all we mean by thermal energy. Chemical energy. That's pretty easy to understand. We need energy between atoms. As you remember from when you took chemistry, we're talking about energy held in atomic bonds. You remember the old bonds. You can see on the right-hand side, there's the covalent bond where it's sharing the electrons. And there's the ionic bond where it's transferring the electrons. Well, when you break those bonds, there's energy being held there. And you can get that energy back by breaking those bonds. And when you get that energy back, that's chemical energy. When you make new atoms, sometimes there's less energy needed to hold those atoms together, and you'll get energy back out. Sometimes you have to put energy in to hold the atoms together. Then you're storing energy inside there. And it can be released through chemical reactions. The glow stick that's in the picture at the bottom, basically when you break the stick, if you had a glow stick, you have to break the stick in order to get it to light up. When you break it, there's two chemicals inside there. You mix them together. There's a chemical reaction. When the chemical reaction happens, it releases energy, and that energy comes out as light. Burning is a chemical reaction with oxygen in the air. Okay. So you can actually see some form of chemical reaction from that. Okay. And you can see the little stick of dynamite we have there. That's a chemical reaction also, and it certainly will be a chemical reaction when the fuse reaches the bottom. Digestion is a chemical reaction too. You're going to actually, the chemicals in your body or in the body of any animal are going to take the food that you eat, and they're going to take it apart, and they're going to break it down so that you can get the chemical energy out of the atoms that are inside of it. They're going to take those bonds apart, and they're going to take the energy out. And so all of those are ways of taking chemical energy. Notice that the chemical energy in the cheeseburger there are stored inside of it before you get it. Your body takes an active role in taking that energy apart, taking energy out of it. Sound also a form of energy. Basically, sound are vibrations that travel through the air or another medium. Sound can travel through. It can travel through a table. It can travel through the ground. It can travel through the water, but it can be sensed or heard. And I don't mean like through headphones or something like that. That's actually electric energy. I mean that it's going to actually, the waves themselves are going to go through some other material. There's a picture of the waves. Now, that's how we sort of think of the waves looking, but that's not really what they look like. They look more like they do in the picture here, where the molecules are actually, if you can see on the top part of that picture, you can see how the molecules are like bunched together. You can see there's dark places and light places, and the dark places, the molecules are all close together, and then they're spread out, and then they're dark places and then spread out. That's what they're really like. They're compressed and they're spread out, compressed and spread out. That's what they're really like in the air. That's what actually happens in between the speaker and your ear. When the speaker makes a sound, if you ever watched a big speaker, it compresses air and then it moves back, compresses and moves back. If you ever seen one of those big subwoofers, you can see it like pushes real hard and then goes back, then pushes hard and goes back. That's what's actually happening. It's compressing the air, moving it back, pressing the air, moving it back. That's what happens in the speaker. But those are vibrations. It does it regularly and then moves through the air, or like I said, it can be through a table or through a sound, or through a water or through the ground, whatever carries it. We're talking about a bunch of mechanical type energies. The first one is kinetic. Those are objects that are visibly in motion. So you can see the kid there is swinging the hammer. When he swings the hammer, it is kinetic energy. It's not kinetic energy in picture 1. When he's picking it up, it's kinetic energy. When he's swinging it down, it's kinetic energy in 2 and 3. Okay. When the roller coaster is in motion, it is kinetic energy also. Okay. Now, the scale is all that makes, in other words, the size of the object makes thermal different than kinetic. Molecules obviously are difficult to see, so molecules are moving objects too, but kinetic energy applies to objects that are easy for us to see. Elastic energy is a form of mechanical energy. It's a stored form, a potential energy form. It is energy that's stored in the change in a material shape. It's usually from stretching a material or compressing it. The obvious examples are rubber band. If you take a rubber band and you stretch it, it's going to store energy because when I let it go, it's going to snap right back. Springs work the same way. Okay. If I compress the spring, it's going to have energy in it because when I let it go, it's going to go right back to its original shape. If I stretch the spring, it's going to have energy in it because when I let it go, it's going to go right back to its original shape, the shape that's on the left-hand side of the picture. And if you have a bow, like Ms. Everdeen in the picture there, you can see that when you stretch the bow, the drawstring back, it wants to go back to its original shape too. We're changing the shape of the string. It wants to go back to its original tension. When you let it go, it's going to push the arrow forward. Gravitational energy is our last form of mechanical energy. It's a potential form of energy also. It's due to the position of massive objects. Remember that gravitational energy is energy between massive objects because of their mass and how it affects the space around it. Okay. Now, it can be because of two planets or the star and planet. You've seen, obviously, the Earth goes around the sun because there's gravitational force between them. But it doesn't have to be. It can be between a planet and the object on that planet. Like, for example, in the picture, there's the space shuttle going around the planet. That's a gravitational form of energy, too. Or between that weight the guy is pulling up, and not between the guy and the weight. Oh, I guess there's some there, too, but it's very small. But between the Earth that the guy's standing on and the weight. As he pulls it up higher, there will be more gravitational energy between the Earth and that weight. Electric energy, this one is pretty obvious. It has to do with the motion of or the attraction or repulsion between electric charges. Okay. Remember electric charges, if you've taken chemistry, we're just talking about the two types. Electrons, they have a negative charge. They're on the outside of the atom. Protons are positive charges. They're in the nucleus of the atom. Much harder to free, but they can be freed. There's a picture. You can see the electrons on the outside. And electrons, again, are much easier to move. We saw that when we talked about the bonding between atoms, that we can move electrons from one atom to another. In fact, in some types of atoms, they're much easier to move. Those are usually ones that are easy to conduct electricity, like metals. Like charges repel, opposite charges attract. You can see in the two electrodes there that there's one of them that has a lot of negative charge on it. It repels those negative charges away from each other and goes toward the other one, the other electrode that has very few negative charges on it. In fact, I think the other one's connected to the ground. So that one will actually take those negative charges, bring them to the ground. So it's going to actually sort of, I guess, in a way, the lack of negative charges is going to attract those over. Now, that covers individual clumps of charges that are moving, individual charges moving, and electric currents as well. So when we're talking about power in the power line or talking about an electric plug or a battery being used, that's electrical energy as well. Magnetic energy is also a type of energy. Technically, it really isn't different than electrical energy, but we're going to call it different. It's due to moving electrons between materials. Moving electrons generate a force also, and that force is a magnet. Okay. It can come from natural magnetic material. You can find magnets in nature. You can make magnetic material too. You can also have electromagnets. Some people, when they're younger, actually make electromagnets, or you can take coiled wire around like a nail and make electromagnets from that. Both of those are acceptable ways. The picture shows the picture has two magnets. It shows the outline of magnetic fields between those two horseshoe magnets. There's no real light between them. It's just sort of an effect meant to show you what the magnet would do to a magnetic particle that's placed at those spots. Also, there's a picture of either an electric generator or an electric motor, depending on what you have. I guess in that case, it would be, because it's a battery, it would be an electric generator. So in that case, the little coil that's in the middle of the magnet would actually be an electromagnet that would repel against the magnet that's there and would spin. So both of those are cases of using magnetic energy. Light energy is a form of energy too, obviously. Okay, they're waves too, just like sound, but they're caused by the vibration of atoms or charged particles. In other words, when you have some charged particle vibrate, it vibrates really fast. That causes light waves. Okay. You can see, like in this case, it's a light bulb. The atoms inside of the little light bulb inside there, they are vibrating really, really fast. That vibration causes light. There's the light bulb, so you can see what it looks like. That's a pretty old-fashioned light bulb. We don't have too many of those anymore, except in flashlights, and even those are going away. They're almost all going to LED bulbs now. We're covering all kinds of light in there. We're talking about radio waves are a form of light. Microwaves, like you use in the oven, or that they use for low frequency broadcasts, say from remote trucks for TV stations. If you see like a local TV station that puts up a little what looks like a satellite dish on the side of their truck, they're not sending TV broadcast waves, they're sending microwaves. Infrared radiation, like the kind that we saw coming from the fire, or that come from like heat. When people have night vision goggles, they're talking about infrared radiation. Ultraviolet waves, X-rays, and gamma rays, all of those are forms of light from our perspective, as it's visible light too. You can see all those in the little spectrum that's shown in the picture. And they all do come from the sun. We can generate those on Earth too, or generate those in our own way, but they can all come from the sun as well. And the last one we're going to talk about is nuclear. Okay. Nuclear is released from the center of the atom. It's not released from the bonds between atoms. It's not released from the moving atoms themselves. It's when we take the center of the atom apart. It's really the hardest type of energy to get. And you can see in this little example of a chain reaction here, you got to take that little neutron at the bottom, you slam it into one of those nuclei, the center of the atom, and it breaks apart into pieces. It lets energy out. When those pieces are taken apart, they bang into other pieces, the leftovers, and then they continue. It's called a chain reaction. That's one way to release it. The other way is called fusion, where you actually take some atoms and make them into slightly larger nuclei, very slight atoms, make them into larger nuclei, and you can get energy out of them. You've seen a lot more atoms to do it. Okay. Nuclear power plants are a place where that happens. Nuclear weapons are another place that we find that in as well. Now, where does the energy go when it leaves one object? Well, it either transfers to another object or objects, or it takes on another form. The example that I wanted to talk about is a coffee cup. Well, a coffee cup has an awful lot of thermal energy in it. Okay, but as your coffee gets cold, that energy doesn't disappear. It goes into the table. It goes into the saucer. and it goes into the air. So the energy doesn't disappear, it just goes to new places. And that follows a rule called the law of conservation of energy. Energy can't be created or destroyed. It just gets transferred from one place to another. Okay. And the rule is that in a closed system, which means that there's nowhere that you can't keep track of that it doesn't go, the total amount of energy at the beginning of the system is the amount of energy at the end. So if I had so much energy in the coffee when I took it out, and I had that coffee in a box that no energy could escape from, a black box, I guess, something where no light could get out, no heat could get out. And I measured all the energy that was absorbed in the box at the end, that the amount in the coffee plus the amount in the box should be the same as the amount that was in the coffee in the box before it started. Now, the form may have changed. It may have become something different. For example, let's say that we had a block sliding across the ground. There was a bunch of friction. Well, I might have to measure the energy in the moving block to start, and then measure the friction, the heat energy at the end. But however I measure those two, I should end up with the same amount. I just have to measure them in a slightly different way. Now, if we look at energy conversions in an object, to do that, we're going to look at where the energy starts. We're going to ID the energy forms that we saw in the other things that we saw today. We're going to look at the purpose of the object, and we're going to ID the energy form, identify it in the object for that purpose. It could be the same as a starting form. Now, there are probably lots of other places that the energy goes, and we can look at those too. But primarily we're going to look at the purpose of what it's for. Then we're going to state the beginning form and the ending energy form. It's pretty straightforward. I'll give you an example so you can see what I mean. The light bulb. Well, there's one right there, the same one we saw earlier. Okay. Well, starting form is, it's plugged into the socket. It starts with electric energy. So that's what it's going to start with. That's what's coming in. And the ending form is going to be light energy. Now you could argue pretty easily with a light bulb with this incandescent light bulb that kind of has a little filament in it. There's a lot of heat energy that goes into that too. I mean, it's not terribly efficient. LED light bulbs are much more efficient. But we're going to say the primary purpose of the bulb is light. We're not trying to heat our home with a light bulb generally, so we're going to say that the primary purpose is light energy. So we're going to say our conversion is from electric energy to light energy. You can look at a bunch of other examples and try those out and see if you can convert from one type of energy to another.